Hello everybody, it is July 2023 and today I want to talk to you about an earlier publication that we made, and this is about the greenhouse effect. Because as we all know, the world is sort of suffering from, or allegedly suffering from, the greenhouse effect that our carbon dioxide that we emit into the atmosphere by burning fossil fuels is actually heating up the planet. So then of course the thing is, what is this greenhouse effect? How can I calculate it? What are the changes? What if I double the amount of carbon dioxide in the atmosphere? What will happen? So I asked a lot of people, I asked around, I read a lot of papers, and I could not find clear answers. So then I was just going to do a complete study, let's say ab initio, from where is this greenhouse effect coming from. And I will tell you one thing beforehand, before we start, is that basically it is not as they say it is. There's a lot of myths in there. There are a lot of untruths in this entire story. So basically we can use the words of, I think it was Mark Twain, that is, the fate of science, a beautiful theory destroyed by ugly facts. So buckle up. I will take probably about half an hour, and it's quite complicated. As you can see, this paper is 41 pages. So of course in this I'm not going to talk about all the details. Please go and then read if you want more details. It is in Atmospheric and Climate Sciences from 2020, so it's already 3 years old. You can also find links to it on stalinga.org, my personal homepage. And I think it is also, it's open access, so you have access to this. Everything is for free. Now let's get started immediately. Let me start with removing one myth, and that is that the greenhouse effect itself, a greenhouse by itself is not working on the principle of the greenhouse effect. Because the greenhouse effect, probably you've already heard it, it's sort of like a radiation balance. In comes visible light, and then this is the Earth is warming up by this, starts emitting in infrared, starts emitting light and wants to shed heat to the atmosphere, and it cannot do this because the atmosphere is absorbing this infrared light. And then the heat is trapped below this atmosphere. Well, the first thing is that is not how a greenhouse itself works. A greenhouse, so this is basically, let me see, this is where we have, this is what we have, what people think is a greenhouse effect. Namely, in comes, let's say, bluish light, and the ground here absorbs this bluish light and then irradiates a reddish light, and this is then cannot escape because this glass here at the top cannot transmit, cannot let through a reddish light. And this is not how a greenhouse works. A greenhouse works by the concept that the Earth is heated, and this heats the air, and the air is trapped physically. No convection can take place, is trapped below this roof. And to show you that this is so, ask any person that has a greenhouse effect if you want to cool down, or maybe when in your car in summer, when you want to cool it down, what do? You open the windows so that the hot air can escape. That is a greenhouse effect that is regulated by that hot air is trapped below a physical barrier. So that is already the first myth that we removed, that the greenhouse effect, the greenhouse does not work with the greenhouse effect. The second myth is that it might be caused by carbon dioxide. And of course I'm going to talk here a lot about carbon dioxide, but it was already Mr. Knut Ångström that said that the total absorption of Earth radiation is very little dependent on the changes in the atmospheric carbon dioxide content, as long as it is not smaller than 0.2% of the existing value. This is basically that the idea is that if you have your window covered by a curtain and it's dark, then covering it with a second curtain doesn't do any difference. So this effect, apparently it's called saturation, this effect happens at, let's say, 0.2 fraction of the current, now of the value of the CO2 in the atmosphere at the time of Knut Ångström. And that is then, let's say, 60 or 80 parts per million. We're at the moment at 420 parts per million, so therefore the effect of carbon dioxide is, according to Knut Ångström, is basically zero. As long as there are other windows that are open, then there is no such thing as a greenhouse effect caused by carbon dioxide. Now, okay, let's see where we can continue now. On the other hand, there is a strong correlation found between carbon dioxide and the atmosphere, and the temperature in the atmosphere. And this was, probably you know this from Mr. Al Gore, but as we know from our lectures in statistics, that correlation is not causation. But anyway, we have to explain this. Also, that if you can explain this by a greenhouse effect, which basically you cannot, there you should also exclude alternative hypothesis for the correlation. And actually, this alternative hypothesis for the correlation is what is called Henry's law. That means that the oceans are, when they're warming up, they release carbon dioxide into the atmosphere. The ratio between carbon dioxide in the atmosphere and in the oceans is a function of temperature. And this is actually, when you look at this data, this exactly 100% explains the correlation between carbon dioxide and the temperature in the data of Al Gore, which is about 800,000 years. So if you want to read more about this, and maybe I will make another video one day, this is called Signal Analysis of the Climate, Correlation, Delay and Feedback, which I wrote in 2018. Okay. So this Henry's law, what I write here, this Henry's law can actually explain the data of Mr. Al Gore. But of course we have other data. So let's take a look. First I have to say Mr. Al Gore showed in his movie a correlation that is 100 millikelvin for every parts per million of CO2 in the atmosphere. So remember the number, 100 millikelvin. But we also have here modern data. So we have here the last, let's say, since 1960, the last 60 years. We also have data of carbon dioxide, that is green, and temperature anomaly, and that is red. And you see that the correlation is quite nice. But don't forget that any two signals that you put on a scale like this, of that we call a transient, functions as of a function of time, then these two, there will always be correlations, and they can either be that they're in sync, or one that is going down in this figure. So that is basically what I always call the stock market graph effect. The stock market is either going from top left to bottom right, or from bottom left to top right. There are no other graphs at all in financial journals, so they contain basically no information. But in the model data, you put it in a correlation plot, and you see that basically we get a nice correlation, and this correlation is 10 millikelvin per ppm. So that is, let's say, 10 times less than the data of Al Gore. So if we want to explain both by the same model, we cannot do this, because we cannot even try to do it in, let's say, but it takes time to adjust this to take effect. This 100 millikelvin per ppm, it will take time. Maybe it will take a decade or something like this, and that is not the case, because the atmosphere itself, in terms of temperature relaxation, has a relaxation time of about 45 days. And we can see this if we take, for instance, in summer, this solid curve is the sunshine. That is a sinusoidal curve, because we have here summer and there we have winter. In the winter it's minimum, in the summer it's maximum. And the maximum of sunlight is of 21 of June. But the hottest day in the year is 21 of July. So it means we have a delay between in a sinusoidal signal between the most illuminated day and the hottest day is 30 days. That means that the relaxation time between the two is about 45 days. So we cannot explain this small value here, because within 45 days, more or less, a couple of times 45 days, it should have been adjusted. So we have here 60 years and not 45 days. So the effect of the greenhouse effect should already have been well incorporated. So we already we can reject basically the greenhouse effect caused by carbon dioxide, because we have two values. of the correlation that are widely different. Therefore, we must reject this idea. There's other data, which I will now show you in a moment, which I will now actually show you. This is actually one more killer argument. For some reason, I put it here at the end of this this paper, because we have, for instance, here the data of 800 million years. So this is 600. I say 800. It's 650 million years ago. We have the transients of both the temperature, which is blue, and the carbon dioxide in the atmosphere, which is purple. And as you can see, they are not correlated at all. So on the scale of 800 million years, they are not correlated. Or actually, when you look at it, they're slightly negatively correlated. And this negative correlation of minus 0.43 millikelvin per ppm, slightly negative. There's long periods of time where this correlation was actually taking place. Also, times when the correlation was positive. But from this, it is obvious that carbon dioxide is not doing anything to the climate when you look at this picture. And we can take it another time scale, and this is, let's say, the human era, let's say 10,000 years, so 10,000, 12,000 years before present. And we can see the same thing again. There is no correlation between the carbon dioxide, which is the purple one here, and the temperature, which is the blue one here. So on this time scale, there is also no correlation, or actually, when you wish to put the correlation, so I fitted a straight line to it, and I get minus 43 millikelvin per ppm. But I would say there is no correlation. This is just a random plot. So we have these things that in different time scales we get no correlation at all, or we get negative correlations. So basically the conclusion is that carbon dioxide is not affecting the temperature. And this you can all find in literature, but here I added one more interesting thing. I compare 3 different cities in Spain. They're at 3 different elevations. That is Sevilla, Cordoba and Granada, and they're quite close together. So they have the same, basically the same climate, at least on average on temperature it should be okay. But of course, above Sevilla, there is more carbon dioxide because it has a thicker atmosphere above it. And Granada, which is at 567 meters, has a much thinner atmosphere above it. But we have been putting so much carbon dioxide in the atmosphere that by now, Granada at this moment has more carbon dioxide above it than Sevilla had in the beginning of measurements. So I plot this everything, and you see that basically there is no correlation. So at this moment, the Cordoba is colder with more carbon dioxide above it than Sevilla was. So that means that carbon dioxide once again is not the temperature factor. And I will come back to this in a moment. But I also want to point out here another interesting effect. Let's see where I have it now. I want to go to. Yes, another interesting effect is that we have here the planet of Mars, and Mars has basically the atmosphere, although very, very thin, it is 95% is carbon dioxide. So Mars has more carbon dioxide than Earth. Above every square meter, there are more carbon dioxide molecules on Mars than on Earth. And as you can see yourself, there is no greenhouse effect whatsoever. So we reject the idea that carbon dioxide is actually temperature forcing. That we must remove. But still, let's see what would be the what would be the greenhouse effect. Now that we rejected that it's from carbon dioxide, we can still calculate it. So let me start then doing what is this thing. So we talk about radiation balance basically. And if we talk about radiation balance, it is about absorption and emission. So the absorption is governed by, normally it's governed by the Beer-Lambert law. So that is the transmission is exponentially decaying with the distance that the light has to pass through in the atmosphere. However, there is a problem with this, because this Beer-Lambert experiments in a laboratory is that the light is absorbed and then never re-emitted. No photons are ever re-emitted. And this means that the light is absorbed and the heat is dissipated in the system that you're measuring. And this is not the case, because we are allegedly thinking that the light is absorbed and re-emitted, so it's a slightly different system. The greenhouse effect is often erroneously presented as being caused by the fact that the absorption depends on the wavelength. That is not the case. What we have to think of is that the light from the sun is absorbed, and it doesn't matter where, how, and by what. The absorbed heat is then immediately redistributed in the atmosphere, and I will show you in a moment that this is exactly the case. It does not matter how and where the solar radiation is absorbed or terrestrial irradiation is absorbed and re-emitted in the atmosphere. If sunlight reaches the surface or not, it doesn't matter at all. The only thing that matters is the amount of radiation received by the Earth. So let's put that into a model. The sun, the Earth is in a solar bath, we could say. This is called the solar constant, W, and the solar constant is 1361 watts per square meter at this distance from the sun. Other planets will get more or less, depending on if they are getting closer or further away from the sun. Note that only the front side of the Earth receives radiation. The back side, of course, at night does not receive solar radiation. That's why we call it night. And when you do the calculation that the average surface received is not this omega, but it's omega divided by 4. And this we call then the sun intensity at the surface of the Earth. And that is then, what is it, omega divided by 4, and I call this S. Now, the idea is that the surface then, which of course is not the case, but I want to explain to you what people think is the greenhouse effect. So the surface is receiving this amount of radiation on average. So we take everything like an average system. And the surface itself is, by emission from Stefan Boltzmann law, which is emitting radiation which is proportional to the 4th power of temperature. So the geo emission is sigma, that's Stefan Boltzmann constant, times the surface temperature T0 to the power of 4. Now if you then do this, that this radiation received is equal to the radiation emitted, then you just can easily calculate that the temperature should be 254.0 Kelvin. I call it here the black body temperature, which is a little bit bad because it's not a black body, because we also include here the albedo, how much is directly reflected into space, the whiteness. So the bigger the whiteness, the less the Earth receives, and the colder, the lower the temperature would be. So forget this about the black body temperature. It's called just how would I call it, the temperature of a planet without an atmosphere. For the planet Earth, it would be 254.0 Kelvin. That's important to remember. The temperature of the Earth is 254.0 Kelvin. And also note that if we place a radiometer into space and look at the planet, this is the temperature that we would measure when we look at the Earth from space. That's, once again, 254 Kelvin is the atmosphere-less temperature, but also the temperature that is seen from outer space. I have to note also that I make a flat Earth analysis. Not that I think that the Earth is flat, but because I want to show you what the greenhouse effect is. If you do a spherical analysis of the thing, you don't get 254 Kelvin, but you get 251.2 Kelvin. So be careful that there is still some kind of discussion about which one is actually correct. But I'm doing it here just phenomenologically so that you will understand what is going on. Also, that different global people are reporting what is the real temperature of the surface, which is also not easy to determine. It's actually very difficult to measure. Some say 288.2 Kelvin, others they say use other temperatures, so we will just use 288 Kelvin. So now look at these two values. We have that it should be, the surface should be 254 Kelvin. You can easily calculate that. And it is in fact 288 Kelvin. So the greenhouse effect of the atmosphere, whatever it is, whatever the method, whatever the mechanism, probably not carbon dioxide, is 34 Kelvin of the planet. Okay, so let's take the simplest model and then say that we take the atmosphere as one block, let's say. That is this. We have the surface, which emits, as we've seen here above, it emits radiation according to Stefan-Boltzmann law. But part of this is absorbed by the atmosphere, and part of it is transmitted. This transmission part I call B. So we have the surface in principle should absorb S, but with the albedo, the whiteness, it is directly reflected into the back into space. What is received by the surface is 1 minus A times S. What is emitted is G, which is Stefan-Boltzmann law, and what is then transmitted into space is the transmission coefficient of the atmosphere times this G. So you can again do the solution and you will get that the temperature of the surface is this equation. What would happen if we double now the atmosphere, the entire atmosphere, not just carbon dioxide, but if we assume that all absorption is due to CO2 and we double the CO2, what will happen then? Well, this parameter B that we can actually calculate, because we have here the temperature, which is 288 Kelvin, and we have all these parameters here, so we can calculate that the parameter B should be 0.21, 21% transmission from the surface into space. Is 21% of the radiation from the surface goes into space, the rest is absorbed. And if we double the amount of atmosphere, then this parameter B is squared. So instead of 0.21, it becomes 0.044. And if we plug that into this equation, then we see that the new temperature would be 298.8 Kelvin. So that means that doubling the CO2, we would add 10.8 Kelvin more. And I did this at a time when it was 350 ppm, so we can get here a climate sensitivity of the atmosphere, which is 300 of carbon dioxide, which would be 30.9 millikelvin per ppm. Once again, then let's go back. This is 3 times more than the one that we observe. Here we had it. It was 10 millikelvin per ppm, and now we measure 30.9 millikelvin per parts per million change in the atmosphere. So this is 3 times too big. But also don't forget that carbon dioxide is only a fractional part of the greenhouse effect. According to people, it's, let's say, a couple of percent, and most of it is caused by water. Let's say 95%. So we should directly divide this one by 20, and we would get 1 millikelvin, let's say 1.5 millikelvin per ppm, which is not something to worry about. At least we should not destroy entire mankind for this small, tiny 1 millikelvin, 1/1000th of a degree. That would not even be measurable. But this is the simplest model you can imagine of the atmosphere as one element, a thick system. But that, of course, is not the case. So what did I do then? I put the atmosphere into thin layers, infinitesimal thin layers, and then do the equations. But I will not bother you with this too much. I will just fast forward. It is again then coming into some kind of, you put it into one parameter, and basically the calculation is the same, but now it's not one block. The atmosphere is not one block, but it is a gradient distribution. The atmosphere is a layer with every layer have a different density and properties and so on. Not so much interesting unless you're interested in that. What is more important is that we do a non-uniform atmosphere, and we use now thermodynamics laws. So we can put it just as a differential equation. Every layer acts a force down and a force up. The force down is the gravitational constant times the density times the area, and the force up is the derivative of the pressure here, proportional to the derivative of the gradient of pressure. And if you then calculate it, you'll get what is called the barometric equilibrium condition, where the pressure is proportional to the exponential of height. Negative exponential, of course, otherwise it would increase with height. Now, what is more important is that this assumes a constant temperature, and this is what was given to me by my astrophysics professor. He arrived at this equation, but of course this equation is wrong because it assumes a constant temperature, and the temperature, as we know, in the atmosphere is not constant. So we should include that. And this is actually very easy to calculate. Now we put the temperature into the equation, the temperature distribution in the atmosphere. Every layer that we have here has a specific energy density, so that is the energy of a layer divided by the mass of the layer, and this is given by the specific heat capacity of that gas, that's the property of the gas, times the temperature, plus the height times the gravitational constant. And if the atmosphere is in equilibrium, all packages should have the same energy. If not, they could exchange energy and redistribute and reach equilibrium. So at the end, if this one is constant for all packages, that means that we can put here the temperature as a function of height. And this is called the lapse rate. The lapse rate then is the differential of temperature as a function of height, and this is given by the gravitational constant, 9.81 meter per second squared, and the heat capacity of the gas. Now the heat capacity of the gas, that depends a little bit. Dry air has a heat capacity, where is it? 1.006 kilojoule per kilogram per Kelvin. And then you get what is called the lapse rate, would be about minus 10 Kelvin per kilometer. But of course the air, as we all know, has water, and water has a very big heat capacity. So what we get is that what we call an effective heat capacity of the air, which is 1.51 kilojoule per kilo per Kelvin. And then the lapse rate is 6.5 Kelvin per kilometer, meaning that if you go about 160 meters into the mountains, you drop 1 degree. So it's going with height, it's going down in temperature. That explains, of course, remember this case with Sevilla and Granada, that is simply the heat equation. Thermodynamics, the heat equation. In equilibrium, the lapse rate is 6.5 Kelvin per kilometer. And then you can again do the complete the differential equation, and you find an equation for the pressure, you find an equation for the density, and you then can plot it. And as you can see here, I have plotted this. This is just simple ab initio calculations based on the properties of the gases in the atmosphere. And you can see here that it fits very nicely. This ab initio calculation fits very nicely with the observations. I took this from the handbook of pilots, and you see that it goes well. And then they assume that above 10 kilometers nobody's flying, so we just keep it constant there, which of course is not true because the temperature is still dropping. And then you can see here also that the barometric equation is not correct. It's not what is observed. The ones that I present here in this work is fitting the data perfectly. And well, I don't have the data for the density, but it also assume it fits. So then we can see that this actually, the atmosphere, listen very carefully, the atmosphere is always very close to thermodynamic equilibrium. The atmosphere is always very close to thermodynamic equilibrium. Meaning that this energy that we receive from the sun is absorbed and redistributed effectively immediately. For the calculation, we can just say that it is absorbed immediately. It doesn't matter where it is absorbed, how it is absorbed, by what it is absorbed. What matters is that it is absorbed, and then it is redistributed immediately. The redistribution is done by convection. That is what we call wind, vertical wind. It's called done by radiation. That is not so important in effect. So this radiation thing is not so important. And something by it's called heat creep, invented by the Connellys and Douglas Cotton. Sorry, I forgot your name. They invented the idea of heat creep. That imagine that you insert heat at the upper atmosphere, then there it is cold. But this heat then, actually, not very well, this heat then is percolating to a place where it is warmer. So the heat goes from a cold place to a warm place. And this seems to be against the laws of thermodynamics, which you learned at school, that heat goes from the hot place to the cold place. But don't forget that this law that you learned is a simplification which only applies to your laboratory, which is a closed-end system, a closed box. The atmosphere is an open box, and there it can go. It will have equal energy and not equal temperature. In equilibrium, you don't have equal temperature, you have equal energy of all packages. And if the small, maybe 1% that it is off equilibrium, we call that weather. So you get storms, you get heat distribution from the equator to the polar caps. This all we call weather. Yes, I'm already nearly, I think, getting closer to the end of the things that I want to say. But now the other thing is that once you realize that the atmosphere is in equilibrium, then if you start, for instance, doubling the thickness of the thickness of the atmosphere or the radiative component of the atmosphere, for instance carbon dioxide, if you think that is causing the greenhouse effect, imagine that it is like this and you double the amount of carbon dioxide in the atmosphere, then what you basically do is that we have in the atmosphere, we have a layer that is at this 254.0 Kelvin. Do you remember what I told you, that when you measure from outer space, this is the temperature that you measure? Well, this thermometer, as you would a radiometer, is basically seeing the level of the atmosphere, the layer of the atmosphere that is at this 254.0 Kelvin. That is what I call the radiative layer, and that is the one that you see from space. That was the one that effectively radiates into space. And from that point on, you have a lapse rate. Maybe it is at 3 kilometers or so, and from that moment on you have the lapse rate acting down, and then you can calculate the surface temperature. So what now if you increase the carbon dioxide in the atmosphere? This layer will actually move up because the atmosphere becomes opaque, and then the radiative layer is higher up in the atmosphere. And that means you have longer distance to have the lapse rate acting on the temperature, and the temperature of the surface will increase. So if the greenhouse effect increases by making the atmosphere opaque to radiation, the radiative layer goes up, and then you have more distance for the lapse rate to actuate, and then the surface temperature increases. So that would be the greenhouse effect of the greenhouse effect agent, whatever you think it is. As I showed you, it's not carbon dioxide. Okay, let's see. I think I already reached the end. Here I put some more very detailed mathematical equations. You can take it for granted or look at it. It's a lot of mathematics with which I will not bother you here. I talked to you about Mars, and then I talked to you about the other things of the 3 different cities in Spain. I talked to you about the different timescales which show that carbon dioxide is not the responsible agent. And basically this is then the end of my talk here. So I hope you now get a better idea of what the greenhouse effect is. It is sort of like a radiation balance thingy, but not very well explained in literature. But I hope that with this rather long talk, I hope you get a better understanding of the greenhouse effect. And once again, let me finish you once again with the words of, I think it's Mark Twain, "The fate of science, a beautiful theory destroyed by ugly facts." Thank you for your attention.